So in this video, we'll take a look at factors affecting the pressure drop during flow in conduits. So here's a simple expression that shows the pressure gradient is proportional to the velocity and to the viscosity, and inversely proportional to the spacing between two plates during flow between parallel plates. And so this is something we could set up and test. And what we'll do is set it up initially with just a fairly simple model of parallel plates, but then we'll change the geometry a little bit and see how this relation, or just a relation of this type, applies when the flow geometry is something other than just some strictly parallel plates. And that'll really be one of the powers of this numerical simulation technique that we've been developing. It'll allow us to take a look at more complicated geometries. And we also want to keep in mind that the pressure gradient is going to depend in an important way on the wall shear stress. So the shear stress is something we saw develop, and we were able to analyze it in the previous video, and so we'll continue to do that. So before we get started here, what I'd like to do is just scroll down quickly to the end of the slides and take a look at something that we'll need to use for this video, and that's setting up boundary conditions on this flow model. And so there are a couple of options. When we set up flow models, we're going to have to specify the inlet and outlet of the flow, so where the flow goes in and where it comes out. And we'll almost always have boundaries that are walls, where the flow is going parallel to the wall roughly. And so you can see in this case, here's this rectangular region. This is the inlet and the outlet, and these are the walls. So in this case, the walls are a default condition of no flow, no slip, it's called. So the fluid is absolutely stationary. There's no flow in any direction right at the wall. But on the inlet side and on the outside side, we are specifying either the flow or the pressure. So that's going to be really how things are going to go. We'll have several options, like I think on the previous slide. Yeah, here we go. So we got inlet, outlet, wall, or an open condition. The walls are going to be no slip by default, and we specify inlet and outlet, and we have to also specify the pressure somewhere. So there are a variety of, here's the pressure boundary condition, and then there are a variety of conditions where we specify the flow. This is the no slip condition. This is the default, where the velocity vector is 0 at the wall. We also could specify the normal velocity to the wall, or the velocity directly, and we might also specify that the normal velocity is 0. In that case, there's no flow that is crossing the boundary. If this is a boundary, for example, and let's say this is a boundary, and we specify this condition, a slip condition, then there would be no flow crossing the boundary. Oops. No flow crossing the boundary, but there could be flow parallel to the boundary. So that's what we get with a slip condition. With a no slip condition, there's no flow either parallel to the boundary or perpendicular to it. So now if we look at these examples, on the downstream side, we'll always specify the pressure in these cases. That will satisfy this requirement that the pressure is specified somewhere. And just for convenience, we'll set the pressure equal to 0. This condition also specifies that there's no viscous stress. The viscous stress is going to be proportional to the velocity gradient. So this condition here specifies the pressure, and it also puts a condition on the velocity. So that will help the solution. And then on the upstream side, we have a couple of options. One is that we specify the velocity and that it's uniform, and this is what we get, uniform velocity. And then we see that as we move downstream, the velocity structure, the velocity profile changes with distance, and we have to go downstream quite a ways before it becomes a condition where the velocity is no longer changing. So one way to have a more uniform velocity is to use what's called a laminar inflow condition on the upstream side. Here we specify the average velocity, but we also specify an entrance length. And what the code does is it sets up a model kind of like this one of this length. So whatever length we specify here, it says, well, I'm going to take a tube and make it that long and let the velocity just develop over that length, and then that stabilized velocity, or what, hopefully it's stabilized after a meter, that velocity I'll then apply as the inlet velocity distribution here. So if we use this kind of velocity boundary condition, we get a velocity distribution that's already going to be quite close to the stabilized velocity distribution for if we have laminar flow. So you can see when I use it for this case that the velocity distribution doesn't really seem to change at all along the length of this tube, and that's because we start off with a stabilized flow distribution. So this will be a good condition to use if we want to study what's happening during what potentially would be uniform conditions here. And then another way to specify an upstream boundary condition is, or an inlet boundary, is with the pressure. So we can use this kind of boundary, a specified pressure and also no viscous stress up here. And if we do that, then we get this kind of a flow distribution. And you can see it looks similar to what we have here, where the velocity profiles are changing in the downstream direction, and there's some kind of a entrance length that was required that we have to cover before we get a velocity profile that is uniform. But nevertheless, depending upon what we're trying to represent in the model, we would want to have one or another of these conditions. We should just keep in mind some of the consequences. Another thing to keep in mind is that when we specify the velocity here and the pressure on the downstream side, that we don't really know what the pressure is up here. And so as a result, we don't know, we're not at least specifying, we're not specifying what the pressure gradient or the pressure drop over this distance is. So when we use this kind of boundary condition, we have to calculate the pressure in order to determine what the pressure drop is. But if we just calculate the pressure here, then we already know what the pressure is here because we're specifying it. So if we calculate the pressure here and we know this distance, we can then calculate the average pressure drop over this interval. Okay, so what we'll have to do is come up with a way to calculate the average pressure over this interval. Because presumably, because the velocity is changing over the interval, over this transverse section, then presumably the pressure is too. Now in this case, we would know immediately what the pressure gradient was because we're specifying it on both sides, but we would have to calculate what the velocity is. Okay, so I've set up a model that will allow us to evaluate this pressure drop scenario that we saw on the slide previously. And the model is very similar to the one that we used in the previous video, with a couple of differences. Here's the velocity distribution, and you can see there's no entrance effect. So I've changed the inlet condition from, here's the boundary condition, and we had previously the velocity was described, and the velocity was given, the velocity was described, it was required to be uniform and specified in that way. But now I'm using this laminar inflow condition that creates the velocity distribution that we would expect for laminar conditions and uses that as the inflow condition. And you can see I have an entrance length here of 1 meter. So that's why I get this quite uniform velocity distribution when I do the simulation. So what I'm interested in doing here is calculating the pressure drop. Okay, so what I need to do is be able to calculate the average pressure up here. Let's see if we take a look at the pressure. Here are some pressure contours. And let's see. And this is what the pressure color flood looks like. And you can see that the pressure here at the upstream side is pretty uniform. And really there's not much variation along the transverse section. So we could just take a pressure up here and a pressure down here. Well, we know the pressure down here is 0. So we just take the pressure here and subtract them. But in general, we don't want to do that because there could be some variations along this width. And so what we want to do is be able to calculate the average and use the average pressure here and take the difference between that and this side. So let me show you how to do that because it's really pretty easy. If we go up here to definitions and right click, then I can go here and take a look at the model couplings. And down here, these are different kinds of integration that can be done on the model. So I selected average and got this one, and I have average and it's a geometric entity of the boundary. So that's variable. So I can select the domain, a boundary, or a point. And what happens then is the average is done over that geometric entity. So I've specified boundary, I specified this boundary, I gave it this name, and so now I have basically it's a function, or what it's called an operator here, that I've named inflow av, and this will calculate the average over this boundary. So what I do then is I can use this function later on in post-processing. Here's the inflow average divided by 0.1, which is the width of the, or the length of the flow dimension and the length of the cell. And so this gives me then the velocity or the pressure gradient. Okay, so that'll be a handy way to implement integrals, and in this case the integral that gives us the average distribution. Okay, so that's a new capability. Now what I want to do is, let's go back here to the PowerPoint. What I want to do is try this out. I just showed a way to calculate this pressure gradient, and if this works, then I should be able to calculate the pressure gradient for different velocities, and the slope should be, it should plot as a straight line, and this will be the slope. Okay, so what I want to do is set up my model so that I calculate the pressure gradient at different velocities. Well, right now I have one simulation that's shown here that is the results for one velocity. And so what I want to do is, and I'll calculate the pressure drop for that situation. This would be well, we'll see what this plot is. This is getting a little bit ahead of ourselves, but let's just say hypothetically that we've just run a simulation for one velocity, and we would calculate one pressure drop. But what we want to be able to do is calculate the pressure drop for several different velocities and plot them together. And in a previous assignment, you calculated the you varied a parameter and you calculated the results several different times. Okay, So it would be possible for us to do several different simulations, save each one, and say calculate the pressure drop for each one of those velocities. But as it turns out, we can do it all at once. And the approach for doing that is to use what's called a parametric sweep. And so what I did was to set this model up just like we did with the previous model. And if I right click here on the study, then I can add this thing called a parametric sweep. And what this allows us to do is to run the model multiple times, varying a parameter. In this case, it's the average velocity parameter. And we'll run models using these different values for the average velocity. Okay, so in order to have this work, the parameter that we're going to vary has to be set up here under global definitions. So we have the average velocity as a parameter, and we give just a default value. But now here, when we run it as a parameter sweep, we're going to start off running the model with a 0.001 velocity, but then we're going to run it, I don't know, 6 or so more times with different average velocities. Okay, and so that's going to give us a good bit more flexibility. So we compute this, the model runs pretty quick. We can see down here the different simulations being done for the different values of the parameters. So now when we are finished, we have the results shown here with this velocity distribution. And you can see that the parameter now is shown here. So we can select the results for these different velocities. And so if I select this one, for example, and plot it, what's going to happen is the color pattern won't change. The velocity distribution will be the same, but the magnitude will differ. Okay, so let's see, we've got 25 here. If I replot it, then it's smaller. Okay, so it does look like we have some change in the color distribution as well. Okay, so that's a parameter sweep. And the thing that this allows us to do now is go down here to this 1D plot, and I made a point graph where I just selected this point here, kind of a nominal way, and I'm plotting this value here, this function that we created that gives me the average pressure on the inflow side, and divide it by the lengths to give the pressure gradient. So that's my y-axis, and the x-axis is the parameter values. Now my parameters are the velocity. Okay, so when I plot this up, I get this plot. Pressure gradient as a function of average velocity, and you can see I get this nice linear plot. And so if I go back to the PowerPoint, then I have pressure gradient as a function of velocity, and the plot is, or the slope is, this grouping of parameters right here. Okay, so that really considerably expands the versatility of what we can do in terms of running numerical experiments, because with this parameter sweep, it allows us to run multiple different simulations by changing the parameters. And if we go up here, we see that the viscosity is a parameter, and this thing called bump rad, this is a parameter that we could use, say, to govern the spacing between the plates. So we can change the geometry as a parameter as well, and use that as a parameter sweep. Now you should take a look at the user guide and read about parameter sweep. It tells you some more of the details. One of the things that we can do is go and we could add another parameter. So if I click plus here, then I add viscosity, and so what I can do is put in viscosity that also changes, and then I can run, the model will run the different simulations for different combinations of velocity and viscosity. So we can end up with many models being run for various different combinations. So it really significantly expands the capability to evaluate how changes in the model parameters affect the results. I think we're probably not going to do that right now. Okay, so this will get you started for the first part of the problem. I think what you need to do is to evaluate how the pressure drop is affected by changes in viscosity. So we'll end here.